Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Valentina Missaglia with us today. Hey, Valentina.
Hi, Frank. Thank you for having me. And hello to everyone who's watching.
Well, thank you for publishing such a lovely article in the APJ supplement. I think that's
Thank you very much.
Valentina, where are you at? What's your geolocation?
I'm actually in Turin, in the northern part of Italy, because I am a PhD student at the University of Turin. I started in November 2019. So if you do the math, I was not very lucky because after a few months of the start of my PhD, the coronavirus exploded. So I'm working from home. Yeah, I'm working from home since March 2020.
Okay.
Yes, and okay, this is sad because the best part of being an astronomer is collaborating with other people. And I'm missing this, but okay, we can do it remotely as we are doing this now. So, but before the corona outbreak, I was lucky enough to spend 3 months in Bologna at the Institute of Radio Astronomy, where I learned to reduce the VLA data that I also used in the paper we are gonna talk about today.
Very cool.
And I worked under the supervision of Dr. Liuzzo, that is actually the third author of this paper.
Okay, very cool. And we will get to that real shortly. So probably you're about 2 or 3 years out from being Dr. Missaglia?
Well, actually in Italy, the PhD lasts 3 years. So in November, I will start the third and last year. So I hope by the end of 2022, I will be Dr. Missaglia.
That is fantastic. Best of luck in that process.
Yes.
So Italy, let's see, what do I know in the news? It's been a relatively hot summer in parts of Europe. I know there's some big fires going on in parts of Europe. So how is the summer where you're at?
Okay, I have to tell you this. I was born in Naples, that is in the southern part of Italy, near the sea. And the summer is completely different from the one we have here in Turin, that it's incredibly hot because Turin is surrounded by the Alps. So it's like a circle of hell during the summer. You feel like you are in hell. Really, I was not used to this incredibly hot weather. So I managed to survive because I'm here doing this interview, but well, this is not what I like about Turin. Yes.
This is awesome. This is well, I don't know if I'll use those words, but I empathize with the heat. So I'm in Phoenix, Arizona. So we are in the desert.
How's the summer there?
It's an interesting summer. You know, we're up around where we usually are. We'll probably hit, it's a little cloudy today, so maybe we'll only hit like 40 C or something like that. But you know, mid 40 Cs, 42, 43 is pretty typical for the summer. The wet season in Phoenix is in the summer. This is when we get our rains. We get monsoons. We get big dust storms called haboobs. Lots of lightning. It's been a little wetter summer than it was last year. Anyway, last year was really dry. So this year is a little bit more return to normal as far as how much like rain and precipitation we get. So it does drive the humidity up a little bit, but yeah, I'm familiar with hot places.
Yes.
That is so cool. Okay. So you already told us a little bit what you like to do for research. So let's go ahead and just get right to the article. And I will do a screen share.
Oh, yes.
Bring up this lovely APJ supplement article. And there might be a bandwidth lag between when I talk.
Here it is.
Here it is. It's awesome. And here we go. Hidden treasures in the unknown 3CR extragalactic radio sky, a multi-wavelength approach. Valentina, take us away.
Okay, so first of all, I want to say that as part of my PhD, I study radio galaxies at different frequencies. So before starting the PhD, I learned to reduce the X-ray data from the Chandra Observatory in the X-ray of radio galaxies. And then during the PhD, I learned to reduce, as I said before, VLA data. And then as a PI, during the lockdown, I submitted successfully 2 proposals, one for the GMRT, that it's a radio telescope in India that works in interferometry, and another one for the SRT, that it's a telescope in Sardinia, Italy, that it's a single dish telescope. So I also learned to reduce GMRT and SRT data. That it's very interesting because they are both radio observations, but with different methods, let's say interferometry versus a single dish.
Okay.
So basically what I did in this paper is a multi-wavelength study of a particular class, let's say, of radio galaxies. So this work is part of a larger project that started in 2008, that is the 3C Chandra Snapshot Survey, where 3C stands for Third Cambridge Catalog, that it's a well-known radio catalog of radio sources. It was performed at 159 megahertz, and then the revised version at 158 megahertz. So they are both low frequency radio catalogs. Right. And they list the most luminous radio sources in the Northern Hemisphere. Okay. So the aim of the Chandra Snapshot Survey was to investigate these sources with Chandra in order to make a statistical study of these sources, and to find counterparts of nuclei, lobes, jets, and hotspots. So in the Chandra archive, there were already observation of the 3C sources, but they were used to make single study of single sources. The sources were studied one by one, not how the whole has this project wanted to do. In fact, I just want to point out that as last author, we have Dan Harris, that passed away in 2015. And basically, he was the father of this project.
Okay.
And in this case, going through all the sources of the 3C, we found that 25 out of the 298 listed in the catalog are unidentified. This means that these sources lack an optical counterpart. There is no optical counterpart. This means that we cannot have a redshift for these sources or an optical classification. So what we try to do is to give a better description of this sourcing using multi-wavelength data, because these sources could have been both high redshift quasars radio galaxies or highly absorbed lower redshift radio galaxies or optically faint LERGs. Okay. So we wanted to give a better, to give a face to these sources. So what we did, we started with a search in the historical VLA archive. Okay. I want to point out that the sources that are published here, the 7 sources, were not the target of the observation in the archive. This means that they were not observed for a long period of time. Yeah. They were just part of the observations. So we tried our best to obtain all the information we can from the observation that we found in the archive. Also, Of course, not all the radio bands were present. There is, of course, a table in the paper that summarized the date of the observation, the frequency, and the configuration. In radio astronomy, configuration is very important because, okay, we know that VLA operates in interferometry, and the dishes can move. So if we have a compact configuration, we can detect the more extended features and vice versa. But in this case, since these were archival observation, we didn't have the chance to select with kind of, yes, we got what we found, basically.
You got what you got. Yep.
Yes, and also to me, apart from the results we got, the most interesting part was that since these were hold data, I had to reduce them manually without any pipeline. Because now radio data are usually reduced using pipelines, but I had to do it manually. And also this is what I was thinking doing the paper, that since I wrote down all the steps I took to reduce the data, I don't know, it could have been interesting to give it to the astronomy community if they want to reproduce the images as I did, or probably make them better. Yeah. This is not related to the paper, but this is something I thought about. I don't know. Okay.
Yeah. Oh, no. So, absolutely. Mm-hmm. Sure.
Yes. So we have observation in LC and X radio band, not to be confused with the X-ray of Chandra, that it's 1.5, 6, and 10 gigahertz nominal bands.
Okay.
And of course, we obtained the flux, we had a radiomorphology with the imaging, and then we also obtained the peak flux, some information about the sources in the radio. Then we moved to the X-ray data reduction. It was a standard data reduction. We used exposure corrected background subtracted Chandra images. Okay. We performed the X-ray photometry full band, so between 0.5 and 10 KAD, and then for the three bands, soft 0.51, medium 1.2, and hard 2.7 KAD. And of course, we removed all the point sources apart from the nucleus, of course. And so we got these flux maps. Then for two sources of our sample, we did the X-ray surface brightness profile because we found some extended emission. But I will go into detail. Maybe it's better when I describe the source itself. Okay. Then we performed also the X-ray spectral analysis of 4 sources that had more than 400 counts in their nuclei. Okay. So we were able to extract the spectra and fit it. We determined the X-ray spectral index. And also we used the model with the intrinsic absorption, and the result helped us to describe better the source, but I will be more clear for each single source. Okay. And then for the 2 sources with the extended emission, also, as I said, we performed spectral analysis, but unfortunately, we didn't get any important result. So if it's okay, I will start describing very briefly, not to be too boring, the single sources.
You're not boring. You're not boring.
Okay. So the first source of the sample is a 3CR91. And as you can see in figure 1, for this source, we have both the optical image, that it's the one in the background. So it's an optical image. Then we have in magenta the contours of the WISE counterpart, so mid-infrared.
Okay.
Then in red, we have the VLA contours of the source that I reduced at 8 gigahertz. Okay. And then in the lower panel, there is the Chandra image. Of course, here the image is smoothed, but when we did the analysis, it was not. It's just to give you an idea. In this case, there is a clear detection of the core. You see there is the core both in the Chandra image and in the radio image. And I want to point out, as I said before, that I reduced the radio data in different bands. So in the appendix, there are also the other radio maps that I created, but cool. I didn't want to make the paper too confused putting all together. So I just used the radio images that can give more information about the radio source. For example, here, because of the radio morphology, we can say that that this source is FR2 radio galaxies. So we try to give a radio classification. Right. Then we see that there is the clear detection of the nucleus, and as you see, there is also a kiloparsec scale. That could be confusing because at the beginning I said we are not able to determine the redshift. Okay, this was possible because in the paper of Glovak et al., it's described a method that uses infrared colors to give a probability of the source to be a quasi-stellar object, a LERG or an ERG. In this case, we got that this source is probably a quasi-stellar object. And then since the source is, regarding the type, we didn't add this plot in the paper, but it exists color plot in the infrared. Okay. That can tell you the kind of source with respect to the position on this plane, making use of the colors in the different WISE filters. I don't know if it's clear. But anyway, since we were able to detect the source in all WISE filters, we were able to use the color plot, and also with the method described in Glovaki, also an estimate of the redshift. Okay. And we can tell that this source is a moderate redshift quasi-stellar object. And for this reason, we did expect the detection of the optical counterpart. Okay. So far, so good. Yeah, excellent. Then the second source is 3C131. So it's figure 2. In this case, we don't have the optical counterpart. We just have the WISE counterpart. And in the Chandra image, okay, probably the colors are not the best, but there is the counterpart of the radio nucleus where the Chandra nucleus is. Also, because we had the WISE counterpart, we obtained a probability of the source to be a LERG, and an estimate of the redshift that is quite high. Then we have 3CR158.
Okay.
Okay, so I forgot to say that in 131, because of the radio morphology, we supposed it's an FR2 radio galaxy.
Okay.
Also 158, it's an FR2 radio galaxy because we detected the hotspots. We have the optical counterpart and the WISE counterpart. And the interesting thing is that in the Chandra image, you can see that there is a detection, X-ray detection, where we have the radio jet.
Yep, that's good.
So we measure the flux of the X-ray counterpart of the jet. We have, thanks to the WISE colors, we have the probability of this source to be a quasi-stellar object. And okay, we were not able to perform a spectral analysis of the core because we didn't have enough counts.
Okay.
For the 3CR390, we can see that the morphology is not very clear. So we were not able to give definite morphology to this source.
Okay.
As in the previous case, we have the radio counterpart, the mid-infrared the optical counterpart, the mid-infrared counterpart, and the core is aligned to the radio core. One interesting thing is that if you look on the west, there is an optical source where there is the knot on the jet in the upper panel of figure 4. Yes, here. It's probably a background source because in the X-ray image, we estimated that this emission is related to the radio structure.
Yeah, you don't get a clean source there. Okay.
Okay, then we have 3CR 409.
Okay.
Okay, well, actually, I forgot to mention that for this source, we had enough counts to perform the spectral analysis of the nucleus, and we obtained intrinsic galactic absorption that is comparable with the, an intrinsic absorption that is comparable with the galactic absorption. Okay. And this is not unexpected because we were able to detect the optical counterpart. Then for 3CR, okay, we are going slowly to the end, so I will try to not to be too boring.
It's all good.
So for 3CR 409, it's still a lobe-dominated source. We classified it as an FR2, but in this case, we were not able to tell the exact position of the core because we can easily tell it's in between the two lobes, but it's not that clear as for the other sources.
Fair enough.
And we don't have the optical counterpart. In this case, we also performed a surface brightness profile in order to estimate the extension of the source. And in the two profiles in figure 7, we have also indicated the position of the radii of the lobes, inner and outer. We obtained a probability of 60% of this source to be a quasi-stellar object.
Okay.
We did the spectral analysis of the nuclei, and we obtained Okay, I have to clarify this. When we, since we were able to obtain an estimate of the redshift, there are actually two estimates, because one is based on the W1 filter and the other one is based on the W2 filter. Okay. When we did the spectral analysis, we of course mix different values of the redshift, of the abundance, and then we selected the best fit value. Of course, we didn't, it was not like a one-shot result.
Okay, good.
And in this case, we had, oh my God, sorry, okay, I'm lost. The intrinsic absorption, sorry. The intrinsic absorption was higher than the galactic one. Okay. And this is why we probably did not detect the optical counterpart. Okay. Then we have and also for this source, since we detected the extended emission as shown in the second panel or figure 5, we also did the spectral analysis of the extended region, and we obtained a temperature higher than 11 keV.
Oh, okay.
Okay, this result could stand for galaxies, for clusters at higher redshift.
Okay, okay.
So what we need is deeper Chandra observation, right, in order to have more counts and do better spectral fitting. Then the last two sources are 3C 428.
Yeah.
We don't have an optical counterpart, but we have mid-infrared counterpart. Mm-hmm. As shown in the bottom panel, we have the X-ray counterpart of the nucleus.
Oh, very nice.
There is a probability of the 70% of this source to be a quasi-stellar object. And we found an intrinsic absorption higher than the galactic value. And so this could be the reason for the non-detection of the optical counterpart. Right. And last but not the least, I think this is the most interesting source of the sample. That is 3CR 454.2 that we classified as FR2. Okay. In fact, we can see what seems to be two hotspots. We don't have the optical counterpart, we have the WISE counterpart, so we were able to have an estimate of the redshift. There is the X-ray counterpart of the nucleus. And then in the figure 9 bottom panel, I have indicated two features, X-ray cavities, that could be due to the radio emission that inflated in the gas. Unfortunately, with the data we have, we were able to give a significance to this cavity. Okay. For the northwestern 2 sigma, and for the southeastern 3.4 sigma, that, as we know, is not enough in astronomy. So also in this case, we need deeper Chandra observation, also because we were not able to give an estimate of the temperature because the values of the fit were unconstrained. Okay. So, but this was our first attempt.
Good.
So in the summary and conclusion, we first give a summary for the whole sample, and then we describe source by source what we found. And actually, the results we got are using both the spectral analysis values and redshift estimate are compatible for what we see from the data. But for some sources, for example, 158, it has a very high redshift. It's 3.16 for the W1 filter and 4.57 for the W2. So it's very high redshift.
Right.
We should use other optical observation to confirm this estimate. That could be wrong.
Mm-hmm.
And I say this is it.
You say that's it?
Yes, I would say so.
Okay. 1 second. Okay. Oh, yes. Okay. And then here in the appendix is where you get down into.
Oh, yes. Yes, there are all the
tables and.
Yes, all the information. And of course, I don't know if it's possible, but if our viewers want to ask some questions, I think they can write in the YouTube channel if I was not very clear, so I can be clearer.
We'll encourage them to reach out to you.
Yes.
Okay, very cool.
Thank you.
Valentina, thank you very much for walking us through
your
lovely supplement article with lots of data to share. Let me ask you, since you hinted at it a few times, where do we go from here, let's say over the next 5 years? Is there additional observing time granted? Is there data in the pipeline that might be coming out for your second paper on your way to your PhD?
Yes.
Is there some theoretical calculations that could be done, etc.? So where do we go?
Okay, so I'm already working on others of this unidentified radio galaxies, because we were awarded Chandra time and Chandra observed the other sources. In fact, as I point out in the paper, we actually got 9 sources, but 2 were being observed while I was working on the paper, so they were not included.
Okay.
So I'm working on that with the same approach. I'm reducing VLA data also. I submitted a VLA proposal for observing this. Yeah, but it was not accepted. So I will try again. Also because you have to wait for the time the configuration is the one you want, as I said at the beginning. So yeah, our idea is to publish all the 25 unidentified and then give as much as information as we can.
Cool. All right, yes. Progress. So I think there's going to be some activity in this field over the next 5 years or so, and it'll be really nice to see some of your future work on this topic.
Oh, yes.
All right, and I look forward to the day when you are Dr. Missaglia. So very cool.
Yes.
Valentina, thank you so much again. And thank you everyone for watching in. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
Bye.